prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. We thank you for the snow. I just pray that you with us today help us to understand Chapter 2 on groups and such, Lord. In your name I pray. Amen. So I think, I don't know, I guess from Chapter 1, the thing it might be worth just reiterating before I get too carried away was the quaternionic representation of space rotations, right? So how did it go? I mean, basically he's like, you have what? You have a quaternion of absolute value 1. He said it's like a complex number, basically something like this. T equals to what? Cosine theta plus u sine theta, where u is an element of IR plus JR plus KR, such that what?
U squared is equal to -1.
Right, u squared is equal to -1, which is a sneaky way of saying that if you look at the length of u as a Euclidean vector, yeah, it's 1, right? All right, and then the claim that I will not work out because it's was assigned as homework essentially was that let's see what they say here. So he says, okay, so if you look at Q, something in this thing that we really should give a name to.
R3?
Yeah. Well, yeah. But it's, okay, it's the R3 inside R4, where R4 is the quaternions that we're interested in, right? Anyway, for that, it is not the case that QT is not generally an element of this space again, right? However, it turns out that if you look at T inverse QT, it is once more, you know, I'm sorry, I give this stupid thing a name. I'll follow your lead. I'm going to call it R3 tilde. To give it an awful name. Oh man, I don't know. There should be a good name for this, but it's the unreal quaternions. I mean that's what it is. It's unreal quaternions. But now, so that was the lion's share of the effort, right? Proving that. Is that fair? Or was that easy? And what was the hard part of this? I guess maybe the hard part is the calculation he has on page 15 where he shows that T inverse VT, where I believe V is an unreal quaternion, right?
Yeah.
Okay.
It's orthogonal to U.
This is an unreal. Oh, this is. Oh, you're right. That's more special. I'm assuming U is equal to 1 when I say that, isn't it? Mm. Yeah. So this isn't even. I better be careful. Let me stop my name calling before it gets us into trouble. Here, I'll just use some slightly unused notation. But T inverse VT, which is, sorry, I am getting to a point here, believe it or not. T inverse VT, which was what? It was like cosine theta minus u sine theta the V, what was V?
It's a vector that's orthogonal to U.
So V is an element of the perp of U, if you will.
Right.
Yeah.
It's a unit vector.
Now that, if U, so like, sorry, so I mean, just as a point of language here, if if U is equal to 1, then V is an element of what we were just calling R3 tilde, right? The unreal vectors, but more generally, it's just in some sort of like volume which is perpendicular to U in the four-dimensional sense of perpendicular. And then,
Well,
I regret breathing that stuff.
we're looking at IR plus JR plus KR, so
IR, say again?
we're looking at these transformations. We're only looking at IR plus JR plus KR, right? Which is like R3 tilde.
Well, let's see here. And choose a unit vector V. Oh, you're saying V. Oh. Yeah.
And you can't be
Sorry.
equal to 1
Yeah,
because
yeah.
U is in IR plus JR.
You're right. Thank you. So both U and V are inside this space.
Mhm.
But, so U and V, an element of IR plus JR plus KR, come on, with V, an element of the perp of U. So like, I mean, all that stuff.
Yeah, so
That
if
just
you
means
were I, then V could be J or something.
Oh, okay, so, right, if U is I, it could be J or K or any linear combination of those. Suitably chosen coefficients, I said, well, yeah, with any coefficients.
And you also get W, which is U cross V. There, maybe jump on the gun.
But,
It makes a basis for.
oh, he's like, let W equal U cross V. Oh, okay, so, goodness gracious. So we have this calculation, UV is equal to minus U dot V plus U cross V, right? I guess I don't need the vectors here. U cross V. So you call this thing W? I mean, I don't know what we're trying to get at here.
That he's making a basis for
IR plus
plus
JR.
plus KR. Also a basis for the plane orthogonal to U axis.
Yeah, I haven't had a chance to work out the proof yet, unfortunately. So I'm a little bit, you guys are ahead of me at the moment. So this has basis, you're telling me. U, I'm not sure I got the ordering right, but U, V, U cross, okay, and that'll be an orthonormal basis. Right-handed, as I have it ordered, as well, since the third is a cross product of the second, of the first two. In any event, through fairly simple calculations, he shows that this is equal to V cosine 2 theta minus W times the sine of 2 theta, right? Some steps missing there, obviously. And so his takeaway message from this is that every rotation of R3 given by an axis U at an angle of rotation alpha can be produced by conjugation of the unit quaternion. So if we want to rotate by alpha about U axis in, let's say, IR, so we're looking at this representation of R3, right? see here, Q maps to T inverse QT, where what? Where T is equal to cosine of alpha over 2 plus U sine of alpha over 2. So that's the big result here. Now it's now, but the thing is, you might ask, okay, so there's a natural question asked then, which I don't think I said enough about last time yet. Oh, guys, remind me, never spray that stuff while the door is closed in here. It's just awful. It's really bothering me.
Spray it into the towel.
I need oxygen. Or I need to start smoking so I can stop and feel better. I don't know. Let's see here. I guess that's probably good. It's kind of like my brother saves money by buying things cheaper than he thought he might buy them. Yeah, I don't think that's really saving money. So this is kind of the big theorem from chapter 1, that part of it. Now, the thing though, you might notice, is that there's not a one-to-one, there isn't quite a one-to-one correspondence between these Quaternion conjugations, right, and the rotations, because if we took what? If we listen to me, if we did, say, S equals to minus T, then what's S inverse? Well, S inverse is just, I mean, if you study how inverse works, it's just, like, it's the same with real numbers, right? If you have 1/3, what's the multiplicative inverse of minus 3? It's minus 1/3, right? So I mean, it's just, S inverse is just minus T inverse. And so if we look at Q maps to S inverse QS, we get, minus T inverse Q minus T, which is T inverse QT. In other words, the correspondence between unit quaternions and rotations is not one-to-one. The quaternion, the unit quaternion T and the unit quaternion minus T, right? These both produce the same rotation in the sense of the conjugation on the unreal part. So, as he points out, he says, this theorem says that rotations of R3 correspond to antipodal pairs of unit quaternions. Okay, so T and minus T are antipodal, kind of like if you have 2 points on the sphere, right? This idea. So like this point is antipodal to that point, right? The ones that are on diameters like that. We also have this though. The product of rotations is a rotation, and the inverse of a rotation is a rotation. So he basically argues, I think I showed that last time, that one's just a simple calculation. Basically, if you have, if you do 2 of these in a row, right? If you go, say by, let me just do it. So if I send Q to T inverse QT, and I send that to S inverse Q inverse grief, T inverse QT, S, then that's equal to what? Oh man, why am I doing that again? Times like today, I really wish I had a chalkboard in here. All right, so that's actually ST. Yeah, you're right. TS inverse by the sock shoes inverse formula, right? And then Q, and then TS again. So in other words, if I take the composition of two of these conjugations, I get another conjugation. And if S and T are unit quaternions, and so is TS. And since, well, he's coming at rotations in R3 a rather weird way. He's saying rotations in R3 are conjugations by unit quaternions. To my taste, this is a rather strange way of capturing what a rotation in R3 is, but, you know, to each his own. He did the work, so that's what a rotation in R3 is, right? So now this proves that two rotations in R3, one followed by another, is again another rotation in R3, as seen through the lens of quaternionic group algebra. So, it's neat. So again, thanks, Daniel, to already have worked that out. You can hand that one in to me. Basically, I just want you to work through the calculation on 14 and 15. All right. One of the ideas he throws around in there is this idea of a reflection. Like, what is a reflection in R4, or I guess anything really? It has something to do with this idea. I think I can erase. It'll be fine. It has something to do with this idea of like there's some sort of hyperplane. So if we're talking about n dimensions, the hyperplane will be n minus 1 dimensional, right? And then there's one other dimension left, right? So I suppose we know that from linear algebra, that if you have Rn, you can break it into the direct sum of a line and then a codimension 1 space, right? So like Rn, we could write something, Rn is equal to what? It's something like the span of U direct sum with what we usually call, I mean, for brevity's sake, I can just call it U perp. I mean, I guess technically in linear algebra it might be like, you have to put the set there because it's a set, you know, or whatever. But you know what I mean. So this is 1 dimensional, and this is n minus 1 dimensional. A reflection, right, would be what? If we're going to talk about, say, like, I mean, let me use a different letter. Let's say S is a mapping from, say, Rn to Rn again, is a reflection of what? What do we insist on? So one of the weaknesses, it's both a weakness and a strength of Stowell's writing, is he doesn't set apart definitions too much, right? Definitions are almost always embedded in paragraphs, so you kind of have to hunt for them. And sometimes you don't realize, you're like, well, why is that true? And if you read the paragraph more carefully, you realize, oh, that was a definition, right? I mean, there's nothing, it's okay, that's the starting point. So beware of that. Okay, so anyway, so it's a reflection of something like what? Like S, let's say S of U is equal to what? How's it go?
Like for a certain hyperplane, it's going to be another.
Here,
There's going to
let's
be another point such that they're both equidistant from.
Here, let's look at a simpler case. R3, right? And let's let U be like that, basically, right? Like let U be Z hat. So what does the reflection do? I mean, geometrically, we know what it does. It sort of takes the point on this side of the plane, right? And
Such that they're like equidistant from the hyperplane and
Right, right.
And it's also the shortest distance to the hyperplane?
Also true, but let's see here, we could write this way, right? This is actually going to be, this point P would be something like, you know, P3 Z hat, and then P1, P2, 0, let's say, okay?
It's
And so,
4
like,
o'clock p.m.
S of P3 Z hat sorry, I'm writing this really weird way.
P1,
P1, P2,
minus P3.
0. Yeah, exactly. It's equal to minus P3 z hat plus P1, P2, 0. In other words, if you look at what it's doing, right, what's the natural definition of reflection? It does nothing to this piece, right? This is just same, right? But the z component gets flipped over. So the rule then, the abstraction of this, is that S of u is minus u, right?
And for anything that's not in U perp, for any B in U perp, it's going to be B.
Right, and then it just fixes v for v in the perp, right? Look at me, I'm writing sets. My stupid singleton again. Stupid linear algebra. Curses and its precision. So that's a reflection. And he has this like, this is peppered throughout paragraphs in the next chapter. He uses this idea all over the place. So I think it's important for us to understand what a reflection is carefully, that this is what it is. Now, mostly we're thinking about this in the context of R4, in the more interesting part of the next chapter. Right? So he'll talk about a reflection in R4. It fixes some three-dimensional volume in R4, right? And it flips that one direction over to reflection. It's easy to see that.
So why is span of view always one-dimensional? Couldn't it also just be a linear combination of the basis elements of Rn?
But U is 1.
Well, I suppose you could also look at maps which fix some like n minus 2-dimensional subspace,
Right.
and take a 2-dimensional, like a plane, and invert it. But this is a reflection.
This is what we're doing.
And it's also interesting, right? Because one of the things that I think is new. I mean, I've always known there's an interplay between rotations and reflections, right? I mean, that's not new to me. What's new to me is thinking of reflections as a way to build rotations, and maybe that's just because I'm not a very good group theorist. But I mean, if you think about, it's already clear to me now. If I took two reflections, right?
Mm-hmm.
Then u flips to minus u, and minus u flips back to u again, right? So two reflections with respect to u, they're going to fix u. So u is going to be an axis. Everything else is fixed in place. And because this is a direct sum decomposition, this means we have a Pythagorean theorem, and you can show that a reflection. I think it follows from this linear algebraic data that S is in fact an isometry. Let's prove it. What would it take for S to be an isometry?
Preserves distance.
Right. Here I was thinking. See, I'm all.
Would it be that u equals negative u? No.
See, that's the thing is I don't know if I want to think. I'm torn. Do I want to show? It's a little bit lost here what I'm doing. Do I want to show this? For like arbitrary points? Or is it that I want to show I can't. Well, I mean, I guess I can just investigate, is either of these true? Yeah. Any thoughts? So here I'm thinking about vectors based at the origin and the angles between them being preserved and the distance between them being preserved. Man,
So the reflection of the distance is the same as the distance?
yeah, that's what I'm wondering. Is it true?
Seems like it would be.
Let's see here. So
Well,
we can write P1 as, let's say, if you let me use this notation, U1 plus P1 vector, and let P2 equal U2 plus P2 vector, where U well, sorry, I guess I should, I mean, U1 and U2 are elements of the span of U, and P1 and P2 vector are elements of the perp, alright? So in particular, that means that, U1 and U1.P1 and U2.P2 and so forth, these dot products are 0. So if I look at P2 minus P1, then I've got U2 minus U1 plus P2 vector minus P1 vector, right? And I can calculate the length squared. I should probably feed this to the reflection, right? I mean, I could prove the little Pythagorean theorem that says that the length, there's the usual orthogonal complement stuff shows that the length of P2 minus P1 squared is the absolute value. Well, fine, it's the length. These are vectors. U2 minus U1 squared plus P2 minus P1 vector squared. You take the dot product of this vector with itself. You take the dot product of this with itself. The cross terms that involve u's dotted with p vectors are 0 because the u's and the p vectors are 0, are orthogonal. You know this, like if you want to calculate the length of a plus b where a and b are orthogonal, it's the length of a squared plus the length of b squared. You ever seen this calculation?
Sure.
It's worth a minute. So if I have a dot b is equal to 0, then if I calculate a plus b, let's say, dotted with a plus b, that will be the length of a plus b squared. The dot product of any vector with itself is its length squared. So you see what this is? This is a dot a plus twice a dot b, using the commutative property of the dot product, plus b dot b. But if this is 0,
Right.
it follows then that the length of a plus b is equal to the length of a squared plus the length of b squared.
It's basically the Pythagorean theorem.
Right,
over again.
It's a Pythagorean theorem done for a pair of vectors in n dimensions. So that's also true here. Okay, so you feed the difference of the points to the reflection. What do you get? I mean,
U1 minus U2.
right. And then the other one stays the same, right? Because the orthogonal complement and the u are themselves, I mean, that makes sense because we're, the span of u is a subspace, u perp is a subspace, so these are again in the span of u and u perp, and there you have it. I mean, of course, the length of, this is equal to the length of u1 minus u2 because it's minus, right? Which is the length of the reflection acting on this, right? Or I mean, I said it like that, but of course this is also what? The reflection is a linear transformation, so this is also, you could also write this, right? So the reflection apparently preserves the distance between points. It's an isometry. Okay. All right. Go on here. I don't know, I need to read chapter 1 again. I need to keep reading. I mean, I found personally I found that with Stillwell's book, like I read him the first time, I tricked myself into thinking I understood. And then I read the next chapter and then I'm like, you know, I didn't entirely understand that last chapter. I need to go read it again. And then about the second or third time I read it, it finally dawns on me, oh, I should have just gotten a piece of pencil and paper out and written some stuff down, and then I'd be fine the first time through, but I'm too lazy. All right, so you guys, any questions before I go on to chapter 2? Okie doke. What do you think? Is that true? The dot product?
Yeah, I think so.
I think that's also true. And I think that if I had a clear mind about what I'd already proved from O'Neill's book, I might understand that these are connected and in fact not disconnected events, because we proved the connection between, I mean, what did I prove? That I forget which we started with. Which one did we start with? Which one did we get to? That's what I can't remember.
We started with the first and got to the second, but I'm not sure.
So we start with just the notion that distance between points is preserved, and then we proved that it had to be coming from something that preserved the dot product.
I think so.
And that I remember we proved that they had to be affine. They had to be like linear plus a translation, composed of the translation rather. And so, all right. So groups. Chapter 2 is about groups. What is a group? Now I know, Daniel, you've had group theory in the process of having it.
I'm taking group theory now. I'm already taking
That's right. And then Bradley, I can't remember. Did you? Okay, so this is the Wild West for you.
I mean, I learned about the general linear group in my thing last semester, but that's pretty much it.
No, well, it's not so different. I mean, so basically here he has just, in the space of about 10 pages, just, as he says, a crash course on groups, right? So a group is a set with an operation that's, as I said last time, I think, the product of two things in the group is again in the group. It's closed under inverses. There's an identity element. If A times B is equal to B times A for everything in the group, then the group is said to be abelian. For an abelian group, sometimes we don't write it as multiplication, like we'll write it as addition. So, for example, vector addition is an example of an abelian. If you just look at, say, for example, the plane under vector addition, the additive inverse is a group inverse. If you add two things together, you get another vector, right?
Right.
Vector addition is associative. There's a zero vector. So, in fact, Rn under vector addition forms an abelian group. Now, he talks in here about subgroups and cosets. So what's let me just try to, since you haven't had group theory, I should spend a few minutes here. We have H, if H is a subset of a group G, right? And H is itself a group. All right, so you have a subgroup, a subset of a group, which is again a group with respect to the group operations. Then we write H, I write H less than or equal to G, and this is my kind of just silly notation for H as a subgroup. A subgroup of G, right? Now, so you also have this thing called a coset. What's a coset? The coset is based on a subgroup. So if I have H is a subgroup of G, then you can do things like GH. Okay, so what is that? You've seen this notation before in other places. I'm not sure. Maybe you have. I think you have. I don't know if I used this notation last semester or not. What here I mean is like G times H. What that means is we just multiply everything in H by G, element-wise. So
and small g is just the element of big G.
right? So this would be like GH such that H is an element of big H. This is the so-called left coset of H. Now you can also talk about right cosets. And yes, here G is a fixed, you know, G is some fixed element of the group. All right. Now, in the context of an additive group, this is the notation for cosets for a multiplicative group. What's the notation if you have an additive group?
G plus A.
Right. So if we're looking at G paired with addition, so in other words, it's an additive group. And by the way, it's a custom of everything that's decent and right in the world to only use additive notation for commutative examples. If you had some professor who used additive notation for non-commutative examples, that would be wrong. I'm not sure which professor might do such a thing, but it seems to me there might be some professor out there. Actually, did he do it? I don't know. It seems like that seems like the sort of thing he might do. But no, he just used a star, and then yeah, okay. But so here, a left coset would be something like G plus H, and a right coset would be something like H plus G, and these will be equal in the case it's an additive group, because in an additive group, addition commutes. So like, you look at it, you've got elements of the form G plus H, but G plus H is equal to H plus G, so anything in the left coset's in the right coset and vice versa. So an additive group or an abelian group has a special property that left and right cosets are no different.
Right. Yeah,
No.
that makes sense. You don't have to worry about left or right.
Right. Now that's not generally true, except for very special kinds of subgroups. So, definition, and this is, I talked to my brother some about this, and he basically is of the opinion that this is not really the right general definition for this. It's just kind of what we tell people in the introductory group theory course, but really the better thing is what I'm about to say is a derived result. But anyway, if the left cosets, if the left cosets are equal to the right cosets, and that's for all G in G, then H is a normal subgroup. It's a normal subgroup of G. And we write H like this. I usually write triangle G. I suppose I might throw an inequality, no, whatever. But normal subgroup. Now there's a theorem, and I think the proof is in Stillwell in pretty good detail, that H is a normal subgroup of G if and only if G inverse H G is it equal to H? It's equal to H, okay. Equal to H for all G in G.
You'll want the capital G for the beginning of the theorem.
Oh, yes I do. Thank you. So, in other words, H is a normal subgroup if and only if it's closed under conjugation by arbitrary elements.
Right.
He's like, okay, well, that's fascinating, but why do we care? The reason we care is because if you look at the cosets that correspond to a normal subgroup, they pick up a group structure by themselves. In particular, you can say, okay, so I'm going to define this new group. What's that?
So being close under conjugation somehow makes it an additive. It makes the right equal the left.
Right.
That's interesting.
Yeah, that actually is in gory detail on page.
Gory detail.
Yeah, gory detail. Pretty gory detail.
He proved it?
Yeah, I think so. Well.
He cheated?
Well, I guess it's sort of on page, maybe he doesn't have that, I don't know, it's kind of around page 28, 27. Maybe he hasn't proved that.
Crash course on homomorphisms.
I could be wrong about him proving that. It may be something else that he's proved. He may have proved actually what I'm about to state, which is that if we look at G mod, so what I'm actually making a definition here, G mod H, the so-called factor, the factor group. All right, so what we're doing is quotienting G by H, where H is a normal subgroup. So what you have here is the set of cosets. So the elements in here are sets in the original group. So like basically we're looking at GH. We'll just use left cosets for the sake of specificity, such that G is in G. This is itself a group. Now how do you define the group operations in here? Well, if I have G1H times G2H, by definition, that's G1, G2H. And if I have GH, and I want to talk about what's the inverse of that, by definition, it's G inverse H. So now the question that's begged, of course, by this definition is how do you know that the definition doesn't depend on the choice of representative for the coset? See, because there's not just one representative for the coset. I mean, you could,
Right.
you can, so that's where the normality is needed in order to show that they're well defined. Let me work through one.
So the coset is the little g times h. That's what the coset is defined to be.
Right.
Okay.
Right.
Yeah. Which is
So-
every little, or the g that you choose times every possible h, which is the subgroup.
Right, right.
Okay.
Now, what was I gonna tell you? So, I mean, here, let's suppose that, suppose you had G1 H is equal to G1 prime H, and G2H was equal to G2 prime H. In other words, I have different representatives, G1 and G1 prime and G2 and G2 prime. And then you could say, okay, so, you know, what if I have G1 prime H times G2 prime H? Well, that would be, by definition, G1 prime G2 prime H, right? But G2 prime H is what? Well, it's
G2h.
G2H, right?
Does that make it G1, G2h, or does it not? So can you do the same thing with the G1 prime? Can you make it equal to, I guess you can.
No, I got the G2 in the way.
Yeah.
I don't remember how I get around. You have to use the normality. I'm only using the left property right now. Oh, sorry. So, okay, so I'll also suppose also that the group is normal. Let me try this again. So first use the normality, which is that G2 prime H is actually H G2 prime, right?
Okay, you can do that.
Yeah, I mean, assuming that H is normal. If H is normal, then G2 prime H is equal to H G2 prime, because the left and right cosets are equal.
Right.
But then, you know, pick your poison, which one you want to do. You know, whatever. So that's G1 prime H G2 by this, right?
Mm-hmm.
And then, but G1 prime H is also equal to G1H G2, and then use the normality again to flip that one, and you get, oh, I probably should flip that one.
Yeah, yeah.
So since I'm working with left cosets of G1, G2, H, using, again, normality. But of course, this on the other hand would be G1 prime, G2 prime, right, by the definition directly. And as you can see, we get that the operation yields the same output, despite the fact we use different representatives. And a similar argument can be made for inversion, on the basis of normality. Now, some people would rather see you guys do arguments at the level of components here, and that might be better, I don't know. But my point here is, of course, not for us to study group theory proper, it's just to use it a little bit as a kind of a guide work for a larger discussion about really specific examples about quaternions and such. Okay, so that's a coset.
Right, so you can't do any of that with quaternions, can you?
Oh yeah, we're gonna do
Oh,
this.
you can?
Yeah, there's
Isn't quaternions not abelian?
Well, that, no, the
Doesn't have to be.
normal subgroups, the normal subgroup idea is defined for non-commutative groups, yeah.
Okay.
Not abelian groups.
I see.
It's just for abelian groups, it's stupidly easy. So, like, I mean, pretty much we work with additive cosets of abelian groups in Calc 2. Things you do with even and odd series are essentially arguments about abelian groups. Like anything can be written as a sum of even and odd. In some sense, that's kind of like using an additive coset, so it's... Anyway. I need to move on. So the next thing up the food, the food, that's the word, the chain here, is the notion of homomorphism of groups. So, homomorphism of groups, if you have a mapping, say from G1 to G2, where G1 and G2 are groups, then if we have phi of AB is equal to phi of A, phi of B for all AB in G1, then this is a group homomorphism. I'm assuming they're both multiplicative groups. You can prove things like, for example, the identity has to map to the identity. So the identity in 1 has to map to the identity in 2. If I have the homomorphism of G inverse, that's the homomorphism. I mean, the inverse in the first group has to translate to the inverse in the second group in this sense as well. See, is there anything else important about homomorphisms I should say, Daniel? Oh, I will say this: when phi is both injective and surjective, when it's 1-to-1 and onto, then a group homomorphism is said to be an isomorphism, and the groups are said to be isomorphic.
If it's bijective.
Yeah, if this is bijective, it's a bijective homomorphism. And so, I mean, two groups are isomorphic essentially means that they're the same group up to some change of notation in some sense. Let's see here. But usually, I mean, a lot of times these homomorphisms are not, even if they're surjective, they may not be 1-to-1. All right. So if you have a homomorphism of G1 onto G2 and it's not 1-to-1, but you still have some sort of sense of there's something about G1 which is captured by the mapping still. It still gives you some kind of version of G1, let's say. Maybe some information's been lost. So that's kind of how I think about current physical law. I think physical, like the physics that we know, is somehow like a homomorphism of whatever the true thing that God did. But it's I don't think it's like half the information is lost. I think it's much worse than that for us. I think we see very, very dim shadows of the underlying order.
Well, we haven't even connected a lot of things in physics.
Right, not even close. But to me, I think this is a useful notion when you start thinking about like analogies to it in physics. I think are interesting, and a good reason to study abstract math, if nothing else. It gives you an imagination you wouldn't otherwise have. It gives you a precision to your imagination that would be hard to capture otherwise. Okay, so that's now in linear algebra.
That makes a homomorphism.
Yeah, homomorphism. It's a homomorphism and isomorphism. In linear algebra, when is a map 1-to-1? linear transformation rather. When is a linear transformation 1 to 1? What is it?
When the result, see if you have two results being equal, it implies that when you put into it,
Ah,
it's the same.
that is true, but that is generically true for any function.
Right.
That's the set theoretic definition of 1 to 1.
More simply, the kernel of the mapping is 0.
The kernel map, right? Only 0 maps to 0. If the only 0 maps to 0 under linear transformation, it's 1 to 1. That is actually a group theoretic thing. In fact, this is a theorem. Phi is a homomorphism of groups. All right. Is injective. It's 1 to 1. If and only if the kernel of phi, which by the way is x in G1, such that phi of x equals to 1 in G2. Okay, so it's you could also write it the inverse image of the identity element in the second group, in the codomain group. If the inverse image of the identity is just the identity, if this is just the singleton containing the identity in the first group, then this is a 1 to 1 map. Otherwise, you can prove that the kernel of phi is in fact a subgroup of G1. In fact, probably the two most important, I mean, there are two important subgroups attached to any mapping group homomorphism. The one is the kernel of the map. The other is the image of the map. So that's another theorem I should mention, Redley. So like here's the theorem. The kernel of phi is, and here's the kicker, it's actually a normal subgroup of G1. And the image of phi, which you could also write phi of G1, is a subgroup of G2. I don't think it's not normal necessarily, and that would take extra structure. But the kernel is automatically a normal subgroup.
The kernel is the same as null space, right?
Right, it's the abstraction of null space to a group.
Okay.
Computer.
My computer is misbehaving. Can I have that? You know, I have precious little battery left, and it's wasting it on this buffoon. See here.
Wait, Andy's not. Oh, I guess he is on.
Is Hillary going to jail? I can answer that. No. All right. Sleep. Yeah. All right. Every so often, it just decides to wake back up again, even after I cover out of the way. Okay. Moving along. So one of the fundamental things then, this is the kernel, let's see, can we prove the kernel of phi is normal? Let's let x be an element of the kernel of phi. What do we need to do to prove it's normal? We need to consider something like y an element of G inverse. Alright.
Right.
I'd like to show that that is a subset. I mean, I'd like to show that y is again in the kernel of phi.
Okay.
So what does this mean? This means y is equal to G inverse, let's say x G, for some x in the kernel of phi, right? which means what?
Phi of y
What's mean phi of x is what first? Sorry,
is equal to 1.
is equal to equal to 1. But phi of y is then what?
Phi of g inverse xg.
Right. So I'm gonna go ahead and use the group. I'm gonna use the homomorphism property. Just get to it. Right. Now, phi of x is what? It's 1, right? And so what we have then is phi of g inverse g. Since 1 times phi of g is just phi of g again. And so of course that's phi of 1, which again is 1. So therefore, y is in the kernel of phi. Therefore, g inverse kernel of phi g is a subset of kernel of phi. And then you just have to show the other inclusion, right? To show that these are equal, what was left to do? Was there any?
No, I was just looking at something.
So if I let z, oh maybe let me make my z more like this. Z, an element of the kernel of phi, then let's see here. Phi of z of course is 1, right? By definition of kernel. And I'm trying to show what? I'm trying to show that G inverse ZG.
And you can split up the phi operation like that, where you have the phi of G inverse.
Oh, here?
Yeah,
I'm using
yeah.
the homomorphism property. So
I
first,
mean the one above that.
well, 1 times phi of G is just equal to phi of G again.
But above it.
Yeah, I'm talking about the line above.
Oh, well, yeah, I'm just applying the group homomorphism property twice.
Right. Okay.
And you can prove it follows for n things by induction, if you love induction.
But down here we're trying to show that the z is of the form like g inverse wg or something.
Right. So what should I do? I may be going down the wrong path at the moment. Do you have an idea? Sometimes it's helpful to just write what you want, right? We want z is equal to g inverse something else, w, g. So that says that the w we want is actually g inverse, right? So there's the man behind the curtain, and you just, to quote a certain Star Trek Enterprise captain, make it so. Let's see here. So we just do what? G inverse goodness gracious, words. Let
Well, we want w to be in the kernel of phi, so we can just do phi of w. We kind of do the same process as we did before.
so help me out here. What should I write? I've got a mental block at the moment.
Phi of w.
I mean, I'm trying to show z is in g inverse.
Right, so but z equals g inverse wg is the same thing as w equals g inverse.
So z is equal to what?
Well, we want to show that it's g inverse wg where w is in the kernel. And so we're trying to show that if w is equal to g inverse, that's in the kernel. So phi of w is equal to 1.
Oh, okay. So yeah, I mean, it's certainly true that phi of w phi of g z g inverse